For this one, it says a compound of copper and sulfur contains 88.39 grams of metal and 44.81 grams of nonmetal. How many kilograms of copper are in 5,264 kilograms of the compound? This one isn't too tricky because you just gotta keep in mind proportions and ratios. But if you don't know which one's a metal and which one's a nonmetal, you might get a little confused here. First of all, copper is going to be the metal. It's going to be the cation in this ionic compound. Sulfur is going to be the nonmetal. So when it refers to copper, it's talking about the metal, that's this. That's Cu for copper. And then the nonmetal is going to be sulfur. So how many kilograms of copper are in it? So we just set up a proportion, known stuff and unknown stuff. So we have 88.39 grams of copper in how much of the entire compound. I would recommend, you don't really have to do this per se because the proportion will hold true, but I'm going to recommend that you add these two up. So what is the mass of the entire compound sample? So the entire sample of this compound of Cu and S together is 88.39 plus 44.81. I get 133.2 grams total in the sample side. I can set that equal to another fraction. This is going to be a direct proportion. I do know another total. 5,264 kilograms is the mass of the total new sample, like this bigger amount. So we want to know how many kilograms of copper are there. And this is just cross multiplication. This times this divided by that will give you your answer. I didn't bother converting grams into kilograms or kilograms into grams because the proportion will hold true. If you wanted to, you could convert these grams into kilograms by just moving the decimal point over 3 times or dividing by 1,000. But it's just really not necessary. You basically just have a small sample and a big sample, and we know how much copper is in the small sample. We want to know how much copper is in the big sample. So you just do a proportion and solve it that way. Number 23, this one says, what volume in liters do 5.12 times 10 to the 28 molecules of liquid ethanol occupy? The density of ethanol is 0.789 grams per milliliter. It's very easy for people to get overwhelmed by a question like this, but you just jump in with dimensional analysis. You literally just write down something that kind of feels right, like the starting amount that's not a conversion factor, and move from there. Now, what does that even mean? Well, a conversion factor is going to relate two quantities. So this is a conversion factor. This is the molar mass, and it relates mass to moles. This is a conversion factor. I'll do it in a different color. And this conversion factor relates mass to volume. That's density. We only have one number that is going to start us off. I also want you to think, as someone who's like made tests and quizzes and stuff like this, think about if you were making a test or a quiz for chemistry and you wanted to give multiple versions to people, right? To prevent cheating and all that. If you were to give this question to 5 people, right? Imagine you want to give almost this exact same question to 5 people, but you need to make the question a little different. You want to keep it ethanol. You can't change the density of ethanol. That's literally just a fact of ethanol, right? You also can't change the density of the molar mass of ethanol. That's a fact of ethanol. These are facts, but it's really easy for me if I were an instructor for me to change 5.12 times 10 to the 28 molecules of ethanol to some other number, like 3.54 or whatever. The number that you feel like you can kind of change and provide alternate versions for is actually usually the one that you start off with. It's kind of like thinking a little bit logically about the background of the test. Because on this test, suppose that this professor wanted to give you a question like this, and they were nice enough to use a question that was almost exactly like this practice test, and they still were going to use ethanol. They would only be able to change how many molecules there are. because they can't change the molar mass of ethanol and you can't change the density of ethanol. So that kind of gives you a clue that you need to start your problem off with the one thing that's not going to be set in the universe's stone, so to speak. So that's going to be 5.12 times 10 to the 28 molecules of ethanol. I guess I'll write it out. C2H5OH. All over 1. You don't want to abbreviate molecules too much. Never abbreviate molecules as MOL. That's the abbreviation for moles, which is a whole different thing. So we have 5.12 times 10 to the 28 molecules of ethanol. That's a lot. It's very helpful if we kind of just get rid of that huge number. To get rid of a hugely, massively ridiculous number, you use another hugely, massively ridiculous number. So I'm going to get rid of molecules of ethanol, C2H5OH. I'm going to go to moles, which is MOL. And I know that there is a relationship between moles and molecules. This is Avogadro's number. This is my first conversion factor. It's not one of the ones given here. There are 2 conversion factors given, orange and green, that I underlined. But you do need to know that 6.022 times 10 to the 23, that's how many things, molecules, atoms, protons, whatever, is in a mole. So currently we've canceled out molecules of ethanol and we have moles. But we don't want to stop there. So put another dimensional analysis conversion factor. This time put moles of ethanol at the bottom. I'm being a little crazy here putting the unit every single time, but it's something that you get into the habit of. So have moles of ethanol at the bottom, and then you have to ask yourself, what can I go toward? Well, you're looking at these 2 conversion factors, and you're like, what's similar about them? Well, there's something great. There's grams that connects it. Molar mass is connects moles and grams, and then density connects grams and volume, which is what you're going toward. So it makes sense here to go from moles of ethanol to grams of ethanol, using, of course, this conversion factor, which says that there's 46.1 grams of ethanol for every 1 mole of ethanol. Cancel out your units here and here, and currently you have grams. This actually is a very valid molar conversion problem right now, because it would be asking, if we were to stop the problem here, how many grams of ethanol is this many molecules of it? And you're like, oh, okay, molecules to moles, moles to grams, that's a molar conversion. But you got to keep it moving though, because we don't want grams of ethanol. We want to go from grams of ethanol to moles of ethanol. Sorry, milliliters of ethanol. Because we want to get out of grams. We know that we're going to have to go from mass to volume, and we have a conversion factor that helps us go from mass to volume, which is liquid volume. Turns out that 0.789 grams of ethanol is actually just 1 milliliter of it. So grams of ethanol are gone and we have milliliters. If this question asked us for the volume in milliliters, we would stop right here. But notice how it says in liters, so you have to go one more step. We're going to go from milliliters to liters. I am going to not even write out the formula anymore because I'm sick of that. But we know that regardless of what the formula is, 1 liter has 1,000 milliliters. So your milliliters are gone. And now your dimensional analysis confirms that the only unit remaining is liters. Run your math through very carefully and you will get an answer. Number 24. What's the molar mass of copper 1 nitride? So probably one of the biggest things people are going to want to review is what in the world is nitride? Like they all kind of swirl, right? So there's a few different ways that ions can appear. Let's say we have nitride, then we have nitrate, and nitrite. With your studying, you do need to be able to differentiate those, because nitride is just a single monatomic anion with a 3- charge. That's a nitrogen that has gained. How do we know it's in with a 3 minus, not a 2 minus or a 1 minus or something. We looked at that way up here. We saw that nitrogen's family just tends to be the -3. That includes phosphide. So going way back down, that's this. Nitrate is one of the polyatomics you have to know. It's NO3 minus. And then nitrite has that ite ending, so it means it has one less oxygen than the 8 ending, so that would be NO2 minus. All that to say, when you know your polyatomic ions versus your monatomic ions, you should not be picking any of those more complex ones. Nitride is really just N3 minus. So let's take a look at this name then. Copper 1, copper is a transition metal, so it's going to be Cu. This particular copper is just a +1. And we just said that nitride is N with a 3 minus. So the first step is to get the right formula. If you do not get the right formula, you will not get the right number because you won't get the right molar mass. You can do the crossover trick if you want, which is really just thinking logically, how many coppers do I need to balance out the absolute charge of nitride? It would be Cu. I'll do it in purple. It'll be Cu with a little 3 and then N. This is the formula for copper 1 nitride. Then you calculate the molar mass, as we know how to do probably. In this formula, there are 3 coppers. So looking at the fact that there's 3 coppers, it'd be 3 times copper's mass, whatever that is. So copper, I think, is 63.55. I just saw it earlier. Let me see. Copper is 63.55, yeah. So 63.55 is copper. This 3 is because there's 3 of them in the formula. We're going to add to that. Don't forget that there's nitrogen, but there's only 1, and a single nitrogen has a molar mass of 14.01, basically. And you're going to do your math here, and you're going to get a number. So this is the math that you do to get molar mass. The number times the actual mass of a single one plus the number times the actual mass of the other one, and you keep going until you're done. So let's see what that actually is going to be. 3 times 63.55 plus just 14.01 about, and you get around 205. There's a lot of places to mess up here. You got to know your ions, you got to know naming, you got to know how to balance the ionic charges, and then you got to know how to do molar mass and recognize that it's not multiply in the middle, but it's add. Number 25 is a percent abundance problem. This one basically is really simple. When you see something like this, just immediately turn your percent abundances into fractional abundances. So this becomes, because you you use percentages as decimal or fractional abundances. So this is 0.9221. This is 0.0470. Wait, yep. And this is going to be 0.0309. I'll tell you that I've seen people mess up in this very first stage. I would recommend you use a calculator. I was brave and just didn't do it because I felt like I could, and I did in this case. But it's really easy to accidentally convert a percent into the wrong decimal. For example, suppose you have 3.09% and then you're rushing and you turn it into 0.309 because you're like, oh, yep, that's right. 3.09% as a decimal is 0.309. If you're just not even 110% sure, just divide by 100 on your actual calculator. We know that this value is not right. There actually does need to be that extra 0 there, because we moved the decimal point over 2 times. All right, so all that is what you need, and you just multiply across. So you take the mass and you multiply it by the abundance as a decimal. Then you add that to the next one. Take the mass and multiply it by the abundance. I'm going to cross out the percentages because I don't want people thinking you're using them anymore. And then you add that to the mass multiplied by its respective abundance. And then you get an answer, so equals something. That thing you get is the average atomic mass of a particular element. So if I were to do this, I can probably just eyeball it, because if you look at this, this thing is much more heavily weighted toward around 28. So I'm looking at the periodic table, and once I have a number, I'm looking for something that has a mass of around 28, and I am feeling silicon. Silicon just feels right, because silicon's average atomic mass is 28.085. So you can verify, but basically just do your math here, and you're going to get average AMU, and then find that on the periodic table. This one says the mass of 3.59 moles of a compound with the formula XF2 is 224 grams. What is the identity of the element X? So for this one, you have grams and you have moles. That should be your very first clue, is to look at your units and see how they're related. If you have this many grams of a compound, and you also have how many moles of it, you can divide them to get the molar mass. So look at these units, grams and moles, and divide them, because you know molar mass has a unit of grams per mole. This literally says divide me. Divide grams by moles. So let's do that. 224 grams divided by 3.59 moles is going to be, I'll do it on my calculator, 224 divided by 3.59 is 62.3, let's just call it 4. 62.4 grams per mole. Now this is looking a lot like a molar mass, because it is. This is actually the molar mass of the compound. Molar mass of whatever the heck XF2 is. So we don't really need this other stuff anymore. I'm going to get rid of it for space. This is important information though, because we can figure out what the other thing is. You actually know that in this compound it is made of two things. It's made of X, which is what we don't know. We don't know the identity of X, but we do know, and oh, by the way, there's only one X in the formula, right? So let me zoom in and say this. This formula only has a single X, so it's 1 X. But the F, there are 2 fluorine atoms, so it's 2 fluorines. Based on what you know about how to calculate molar mass, as we just reviewed up here, you can set up an equation for the molar mass calculation. You actually know the molar mass. That's like really helpful. So let's block this off, and then let's set it up. In this case, if you want to think backwards, you know that molar mass is equal to the number of the elements that you know times the number of the element times the mass of it, plus the number of the other element times the mass of it, and you keep going. So that is going to look like this in this case. The 62.4, that's the molar mass, is going to be equal to, and there are only 2 elements in here, right? So let's do those 2 elements color-coded. There is one element, there's only one atom, I should say, of we don't know. We don't know what the molar mass is. This is the unknown molar mass of the unknown element. Once you find the molar mass of this mystery element, you can find what it is by looking on the actual periodic table. But let's just come back to that. Then we do have it known that we have 2 fluorine atoms. Now the periodic table will tell you what fluorine's real molar mass is, and it's about 19. So then you got to just do some algebra here. If you want to make it very algebraic, just make this an M. And then let's see what this actually is together. Luckily for us, 1 times M is just M, so I can get rid of all that. And move this way, and then move this way. Okay, good. So 2 times 19 is 38. And we're subtracting that from 62.4. So 62.4 minus the 38, which is this stuff. So this is 38. is going to tell us that M, which is the molar mass of we don't know, is equal to 24.4 grams per mole. So then you're going to look up on the periodic table, find what the thing is with 24.4 nearly, and it's going to be magnesium. And these numbers are going to be approximate. Magnesium's molar mass is really about 24.3, but 24 point something is going to get you there. That's why it's magnesium. It certainly can't be copper, because copper's molar mass is like 63 or something like that. Anyone who thinks it's copper probably just didn't go far enough in the problem. Same thing with the other stuff. Nothing makes sense except for it being magnesium. Another clue is that all of these are metals. So if you think about how your ionic charges works, you know that fluoride is -1, and there's 2 of them. That's a total amount of -2 charge, which means you must have a +2 charge. So whatever this mystery element is that we just figured out is magnesium, it has to be something that can have a +2 charge typically. So that's going to be something like calcium, which is in the same family as magnesium. Could have been a copper too. We just don't know. But that's one of the things you can kind of think about, how everything is connected. Number 27. Which pair of particles has the same number of electrons? This is a good question because you have to think also about ions in general. Let's take a look at the first one. The first one is going to be fluorine, or the fluoride ion, versus, so to speak, the magnesium cation. So we have an anion, which has a negative charge, and a cation, which has a positive charge. So let's see, fluorine, any fluorine is going to have, I'm trying to use this on my phone. How many? I think it's 9. Yep. It's going to have 9 protons. I recommend that you just write out how many protons everything's going to have. Fluorine is going to have 9 protons, and magnesium will always have 12 protons. Oh, and I should probably say, I don't know if you learned this term in your particular class, but when something has the same number of electrons, that's considered isoelectronic. If they have the same electron configuration. But that's just like a term you might hear about later. So in this case, we have 9 protons from the fluorine, 12 protons from all magnesiums. But then you got to do some math because remember, these are ions, so they lost or gained electrons. If it has a negative charge or more, that means it gained 1 or more electrons. So there are going to be plus 1 electron. There's going to be 10 electrons here. Notice how there's a net negative charge. There's 1 more negative than there is positive. That's why it has an overall charge of -1. So that means that this fluoride ion has 10 electrons. That's what you're looking for. This this magnesium ion would have 12 protons and 12 electrons if it were neutral, but it lost 2 electrons. Whenever something has a positive charge, you're subtracting a negative, remember. So since it lost 2 electrons, it only has 10 electrons. So far this is looking good. These two things are isoelectronic in the sense that they have the same number of electrons. But just want to verify a couple of other ones so that you're sure about how this process would work. So let's take a look at the bromide ion and the selenium and a neutral selenium. So bromide normally has, or always will have, check it out, 35 protons. Compare that to selenium's always having 34. And then we want to do some math to figure out how many electrons they have. Let's start with selenium actually, because if selenium here is neutral, notice how there's no plus or minus there, it's also going to have 34 electrons. But this bromide ion, which normally has 35 protons, has a net charge of -1, which means it gained an electron relative to the number of protons, which means it has 36 electrons. These two numbers are not equal, so that's not a good answer choice. Neutral neon and neutral argon clearly don't have the same number of electrons because they're just not even, And then Al3 plus and P3 minus, probably worth seeing as well. Aluminum, with a 3 plus charge versus the phosphide ion with a 3 minus charge. Aluminum always has 13 protons, but it lost 3 electrons, so it would have 10 electrons. The phosphide ion, phosphorus atoms always have 15 protons, and notice here it says it gained 3 electrons, so it went from 15 up to 18. So now it has 18 electrons. Those aren't equal either, obviously, so that's also not a good answer. So that's how you do questions like that. This question is asking how many sig figs should be in the final answer. There are 2 rules going on here. The top part is addition subtraction rules. Remember that I call those PDDs, which are post-decimal digits. Just look at the digits behind it. Both of them have 1 after it. Then you look at the stuff in the denominator, and notice how that's all multiplication. So here we have 5 sig figs, here we have 6 sig figs, and here we have 3 sig figs. So your answer certainly cannot have more than 3 sig figs. But then you have this going on up here. So remembering your rules of addition and subtraction, you can only keep 1 digit, and it's only 1 digit anyways, after the decimal point. So my tip to you is do the top part, get rid of the subtraction aspect, and just keep that purely exactly what it is. So that's going to be 154.6 minus 5.2. That simplifies to 149.4. And then you divide. And look at the fact that your weakest part only has 3 sig figs. And that's going to be a pretty big clue. Number 29. This one says the Toyota Prius, a hybrid vehicle, has a gas mileage rating of 52 miles per gallon in the city. How many kilometers can the Prius travel in the city on 15 liters of gas? Dimensional analysis again. So, what do we start off with? Just like that logic I was telling y'all to think about with the ethanol question. This is a set in stone number, as well as these conversion factors. So this is actually a conversion factor as well. So you have 3 conversion factors, one that relates miles and gallons, one that relates miles and kilometers, and one that relates gallons and liters. But we do have something that's kind of a limiting parameter here, which is how many liters of gasoline does the car even start off with? So let's start off with that. We have 15.0 liters over 1. Convert your liters into, pause and think, what do I want to go to? Which of these conversion factors relate liters to anything? And it's this one. So this conversion factor, if I want to color code it, I'm going to go from liters to gallons. Turns out that 1 gallon is almost 4 liters. Keep moving with your next conversion factor. Now we have gallons. So if you want to cross out liters, go ahead. We have gallons currently. We want to go from gallons to, we want to break out of volume. We've gone as far as we really need to go with volume. But now we have something that connects volume with distance, which is gas mileage. We're going to go from gallons to miles. And that 52, this basically says, remember, say it as a sentence, 52 miles per gallon. This car can go 52 miles on every 1 gallon of gas. Cancel out gallons. You currently have miles. And only one more step remains, which is go from miles to kilometers, because that's what we're ultimately asked for. And then this is your final conversion factor, and this conversion factor is going to be given here. And that's going to be 1 mile is about 1.61 kilometers. These are all 3 sig figs. That's why all your answers are 3 sig figs. Notice the small details. And when you do your math carefully, you'll have your answer. Number 30. What mass of phosphorus trihydride, which has a given molar mass, is produced when 7.52 grams of hydrogen reacts with excess phosphorus? luckily they are telling you what phosphorus's formula is here, and they give you the formula as well. This is stoichiometry. So the way that you start this off is you look at the quantity given. We have 7.52 grams of hydrogen. So let's write that. 7.52 grams of H2. Hydrogen is a diatomic element when it's in its pure state. Remember that in future situations. In this case, you don't really need it, but you should definitely know what your diatomic elements are. So you have 7.52 grams of hydrogen over 1. Go from grams of hydrogen to moles of hydrogen. The mole is the goal. Now this is going to be the molar mass of hydrogen, which is about 2.01-ish. That's hydrogen diatomic, so it's H plus H. And currently we've gotten rid of hydrogen grams and turned it into moles of hydrogen, which is H2. Now looking at this problem, it's gonna get some people. If you look at this equation, you might notice that it's not balanced. You've got to balance it. You can bet that one of the incorrect answers will be the stoichiometry of this with incorrect coefficients. So basically, if you were to do this problem without balancing it, you get the wrong answer. So you have to balance it. If you balance this, you can put a big 3 in front of the H2, a big 2 in front of the pH3. There's an invisible 1 in front of P2, and you're done. So we're going to go from moles of hydrogen to moles of, it asks what mass of pH3, so we're going to go to pH3. Now, as we said before with stoichiometry, when you have moles of one thing over moles of another thing, and you have like basically moles over moles, the relationship between two different species and their moles is the actual chemical reaction itself. We didn't balance it just for fun, even though you might think it's fun. We did this to get those coefficients for a reason. And the coefficient in front of H2 is a big 3. The coefficient in front of pH3 is a big 2, and that relates those quantities using the balanced equation. When you do stoichiometry, you have to use the balanced equation to relate your moles over moles. We are almost done with the stoichiometry. To do one more step, to convert your moles of phosphorus trihydride into grams of phosphorus trihydride. At any time, just remember, when you're relating moles to grams for something, or grams to moles, just the opposite direction, you use the molar mass. And it was nice enough of them for them to give us the molar mass of phosphorus trihydride. It is 34.03. That's the mass of every mole of it. Cancel. Done. Do your math. And you have your answer. This was not a limiting reactant problem because notice how it said we have excess phosphorus. Now, what if it didn't say that? What if it gave us an actual quantity of phosphorus? So we had this amount of hydrogen and then some literal number for the amount of phosphorus and it wasn't excess? Then you would have to do stoichiometry again and compare your two amounts. Remember, that's a limiting reactant problem. In this case, it's not because you have excess for one of them. For number 31, it says aluminum and oxygen react according to the following equation. So you have 4 moles of aluminum reacts with 3 moles of oxygen to produce 2 moles of aluminum oxide, which you may recognize from that bauxite ore question. If 4.6 grams of aluminum with a given molar mass reacts with excess oxygen to produce that much, so 6.8 grams of aluminum oxide, calculate the percent yield. These are fun. First of all, you should not be getting percent yields above 100 unless you made a mistake. As a reminder, percent yield is equal to the actual yield, how much you really make in practice, divided by the theoretical yield, which is how much you should make based on the stoichiometry, times 100. Whenever you do stoichiometry, you are getting the theoretical yield. So let's move on with it. It says 4.6 grams of aluminum. That's one of your reactants. So we're going to put 4.6 grams Al over 1. Put grams of Al at the bottom because we don't want it, but it really is obvious at this point that we're going to go to moles. And 1 mole of aluminum is 0.0 grams of aluminum. So we just did a molar conversion from grams to moles for aluminum. Then you're going to go from moles of aluminum to moles of whatever you care about. Now we're looking for the percent yield of the reaction. So we're in reality, I guess I'll do this here in green. The actual yield is 6.8 grams of Al2O3. We are doing stoichiometry right now to figure out the theoretical yield. It's very common for people. It's common for people to think that this is the theoretical yield and you get like the inverted number. So let's put Al2O3 here. At this point, you're probably used to figuring out that in stoichiometry, the way that you relate moles to moles for two different things, so we have one thing and another thing, is to use the balance equation. Look at these big numbers. Those are the molar coefficients. The molar coefficient for aluminum is just 4. And the molar coefficient for aluminum oxide is a big 2. Turns out we didn't even need oxygen in this case. Matter of fact, oxygen was excess, so it makes sense that we don't care about it. So moles of aluminum are gone. And now we have moles of aluminum oxide. Convert that into grams of aluminum oxide. And when you do that, you're going to get, do they give you the molar mass? They do. That saves us some time. You could do it on your own, but it just saves us time. So 1 mole of aluminum oxide is 102 grams of aluminum oxide. All right, then you do your stoichiometry. Once you do the stoichiometry, I'll do it real quick. We're going to get the theoretical yield. So it'd be 4.6 times 1 times 2 times 102. Divide that by the product of 27 times 4, and we get 8.68, repeating, so let's call it a 9, grams of aluminum oxide. This is your theoretical yield. Just remember that. Whenever you do stoichiometry and you get a number, that's your theoretical yield. So plug that into your equation. So let's take this equation, duplicate it, and just plug in our numbers. We know all of our values now. From the information in the problem, we had 6.8 grams. From the stoichiometry we just did, we have let's just call it 7. So 6.8 divided by that. Don't forget to multiply by 100, and we get about 78%. So that's the percent yield. So 78%. And that hopefully helps with the chemistry test.